Classification of microwave tubes, two types here, O-type tubes and M-type tubes. So O-type tubes are also called as linear beam tubes, and M-type tubes are cross-field tubes. So in linear beam tubes or in O-type tubes, it's a beam nothing about field components here, electric field and magnetic field. We know that when you go for the microwave or electromagnetic wave, it is having the two field components, electric field and magnetic field, and those two are perpendicular to the wave propagation, and always those two are perpendicular and those two are perpendicular to the wave propagation. But here in linear beam tubes, the electric field and as well as magnetic field both are parallel to each other. Right? So electric field and magnetic field parallel to each other. And coming to M-type tubes, here both are perpendicular to each other. Electric field and magnetic field are perpendicular to each other. Next, these O-type tubes are again classified into cavity resonators and slow beam structure or slow wave structure. Cavity resonators and slow wave structures. Again, the cavity resonators is nothing but these are reflex klystron and Klystron amplifier. So what I want to say is the examples for the cavity resonators, reflex klystron and the Klystron amplifier. Yeah, these two are very important. Klystron amplifier, reflex klystron. The reflex klystron can be used to generate the microwave signal. That means it can be act as an oscillator. So reflex klystron is an oscillator. So two cavity klystron. That means you can say that klystron can be act as a oscillator and klystron can be act as a amplifier. And coming to slow wave structures, again here two types here, forward wave and backward wave. And the examples for the forward wave structure is TWT. This is traveling wave amplifier. Traveling TWT nothing but traveling wave tube amplifier. And coming to backward wave. So here again we are having backward wave amplifier and backward wave oscillator. So this is that's it about the classification of microwave tubes. So O-type tubes and M-type tubes. So here O-type tubes nothing but klystron amplifier and reflex klystron and the traveling wave tube, backward oscillators. All these are the O-type tubes. And coming to M-type tubes, the M-type tubes are cross-field tubes, and the example for the M-type tube is magnetron. Here I didn't mention actually. Here one of the example for this M-type tube is magnetron. So according to our syllabus, you have to learn about the Klystron amplifier, reflex klystron, TWT, and magnetron. These are the four topics mentioned in our syllabus. Right? Next, first put the guys among all these things. First, I want to give the explanation about the two cavity Klystron amplifier. Now put the heading as two cavity Klystron amplifier. Now only I told that Klystron is a device. It is a microwave device, and it can be used to generation purpose and amplification purpose. That means we can say that a Klystron is a vacuum tube that can be used either as a generator or as an amplifier. So used either as a generator or as an amplifier, yet for of power at microwave frequencies. Amplifier of power yet high frequencies, that is at microwave frequencies. So this is the microwave device actually, Klystron. So the Klystron that can be used for amplification purpose, that is two cavity Klystron amplifier, and a multi cavity Klystron amplifier is also available, but according to our syllabus we are having only two cavity Klystron amplifier. And the Klystron that can be used for generation purpose is known as the reflex Klystron. Okay. So first about the amplifier, that is two cavity Klystron amplifier. So put the heading as two cavity Klystron amplifier or two cavity Klystron amplifier. Don't confuse. In some cases you will find like Klystron and some places Klystron. Don't confuse. Two cavity Klystron amplifier. So this is the two cavity Klystron amplifier diagram. So look at the screen, or look at your WhatsApp groups. Already I shared the image. First about the description of this Klystron amplifier, and as the name itself indicates that it can be used to amplify the power at microwave frequencies. So it is having two cavities. So look at the two cavities. Those cavities are input cavity and output cavity. So input cavity, and this is the output cavity. And input cavity is also known as buncher cavity, and output cavity is also known as catcher cavity. And here this is a vacuum actually. So it's like it is a vacuum tube, and these are the gaps. Here I mentioned that this is the gap A and this is the gap B, and this is a cathode actually. Here cathode, and here the plate. So already we know that cathode can generate the electrons here. So here I want to use the electron gun. So look at this, it's focusing electrodes. So from this, actually the electrons are generated or delivered from this electron gun, and those are travel like this. Okay, those are travel like this, and those can be collected by the collector. Those can be collected by the collector, and already we know that always electrons can be attracted by the positive one or positive charge. So collector is having the positive charge. And look at this battery also. So negative is connected to electron gun and the positive is connected to collector. So it is the positive charge, and this one is negative charge. And once again I am repeating, two cavities, buncher cavity and collector cavity. And it's actually what is my main purpose here? I want to amplify the signal. I want to amplify the high frequency signal. I want to amplify the high frequency signal. So I want to amplify the RF signal. So in order to amplify that, first you have to give the RF signal as an input. So in order to give the input, so I want to enter this RF signal into this input cavity through the loops. So so this is the coaxial loop. So once again, I want to enter this RF signal. That means what I want to amplify that signal. I want to enter into this input cavity through the coaxial loop like this. Okay, that means it is coming like this. It is coming like this. Right. Next, the space between these two cavities, that is known as the drift space. The electrons are drifted through this space. Actually, that's why it is known as the drift space. And these two are the bunches, electron bunches. That means the electrons are coming from this electron gun. Those can be travel like this. those can be travel like this. At some place, those can be formed like a bunches. That is more number of electrons at one place. So those places are known as electron bunches. So this is the electron bunch. This is also electron bunch. That means you can say that at this position, the electrons can be appear like a bunches. So more number of electrons in one place. And finally, all these are collected by the collector, and the output signal, RF output signal, can be collected by this catcher cavity or output cavity. Again, here one coaxial loop. So the RF output taken from this coaxial loop in the output cavity, and the RF signal is entered into this input cavity or buncher cavity through this coaxial loop. Clear about the description? Description of this two cavity Klystron amplifier.
Yes, sir.
Right. So this two cavity Klystron amplifier, which is basically a velocity modulated tube. So here one of the important definition is velocity modulation. No problem. I will give the definition of velocity modulation after completion of operation. Here a high velocity electron beam is formed, focused and sent down along a glass tube through an input cavity. Okay. High velocity electron beam can be formed and focused and sent down along a glass tube through an input cavity. This is the input cavity. A field drift space in an output cavity to a collector electrode or anode. This finally, this electron beam can be passed through the input cavity, drift space, and catcher cavity, and finally to the collector or anode. So always we know that the anode is kept at the positive potential with respect to the cathode. Now the electron beam passes through a gap A consisting of two grids of the buncher cavity separated by a very small distance. So the spacing between these two bunches, so separated by a very small distance, and two other grids of the catcher cavity with a small gap B. So these are the grids of the catcher cavity. So this is the gap. This gap is gap A and gap B. Okay, that's it. Just about the description. Now I want to go for the operation. So in order to know the operation, or in order to explain the operation of this two cavity Klystron amplifier, you have to go for the applicate diagram of a Klystron amplifier. Applicate diagram of a Klystron amplifier. I want to open the applicate diagram. Just wait a while. So applicate diagram of a Klystron amplifier. When you look at the diagram, you will find that EL, ER, EE, and up to like that. So here I will give the clarity about these three things. So now I told that when you look at the Klystron two cavity Klystron amplifier, the RF signal is entered into this into the gap A through the input cavity. So here I want to assume that this is the RF signal. This is the RF signal. So positive amplitude, and this is the negative amplitude, and here this point is 0. I'm repeating once again. Please tell me. So this is the point C. I want to assume that. 3 points here. Don't think that only 3 electrons coming from the electron gun. Don't think like that. So multiple number of, so many number of electrons are coming from the electron gun. It's not possible to write all these electrons. For that reason, I want to take only 3 electrons. Okay, one is at the highest voltage, and another one is at the low voltage, like negative voltage, negative high. Another one is at the 0 voltage, right? So see the, look at the point B. So look at the point B. At point B, what is the voltage? What is the amplitude here? 0. 0, okay? At point B, voltage is 0. So see here, what happens? Electrons are coming from the electron gun. Listen carefully. Electrons are coming from the electron gun. So like this, moving like this, moving like this. Suppose. So electrons are coming like this. The electrons are coming like this actually. So at this point, here what happens? RF signal is coming like this. Now here RF signal combined with these electrons, right? RF signal is combining with these electrons. So because of this RF signal, the velocity of the electrons changes. So the reason is Here RF signal nothing but this is not the having constant amplitude. It is a high frequency signal. Suppose like this, it is having the different amplitudes. It is having different amplitudes. For example, the RF signal is having only one amplitude. Suppose if it is a DC signal, for example, if it is a DC signal having the 2 volts or having the 5 volts, what happens? Here the electrons are moving like this. At this position, all these are multiplied with this 5 volts. At that time, no problem. But here, what happens? These electron beams are multiplied with the RF signal, and this is not having the constant amplitude. The value which changes sinusoidally. So it's not possible to write all these amplitude levels. That's why I want to take only 3 levels. There is the maximum value, the minimum value, and this reference point. So here what happens? Whenever all these electrons are available here and the RF signal is here, whenever electron is multiplied with or combined with this point, so meaning of that is combined with combined with this B point is combined with the B point. So B point nothing but amplitude is 0. So amplitude 0 nothing but there is no effect on that electron. The electron is traveling with the same velocity. Once again, so what I want to say is, whenever RF signal is touches the electron at the point B, the amplitude of the RF signal is equal to 0. So there is no problem to this to that electron. There is no change in the velocity of that particular electron. So that electron can be travel with the same velocity because no effect for the electron from the RF signal. That's why I want to assume that electron is the reference electron, ER. The electron is the reference electron VR, and I want to assume that velocity is equal to V naught. So same velocity, right? Next, again, so many electrons are available. Maybe if the electron is, so coincides with the positive value, then what happens? So positive value nothing but more acceleration, and negative value nothing but less acceleration. So I want to give the points very well. At point B, on the input of RF cycle, the AC voltage is 0, right? And going positive, at this instant, the electric field across gap A is equal to 0. So gap A nothing but that is from the Klystron amplifier. And an electron which passes through a gap A at this instant is unaffected by the RF signal. Let this electron be called as a reference electron. Okay, that electron is reference electron, ER. Now which travels with unchanged velocity because no effect on this electron beam with the RF signal. So and that velocity is V naught is equal to root 2 EV by M. Already we know this formula where V is the anode to cathode voltage. Next, coming to point C. At point C of the input RF cycle, electron which leaves gap A later than the reference electron ER. So one is with the same velocity, another one is later than the reference electron. So after the reference electron, that is called the late electron, and that is subjected to maximum positive RF voltage, and that is travels towards gap B with increased velocity, because here what happens, the electron is combined with the maximum voltage of the RF signal. So maximum voltage of the RF signal, and that travels after the reference electron. So that's why it is known as the late electron. But that is traveling with the high velocity because that is combining with the high RF voltage. That's where I told that increased velocity V greater than V naught. Okay. Point here, and this electron tries to overtake the reference electron ER. This electron tries to overtake the reference electron ER. Is it true or not? Because ER is traveling. With the velocity V naught, with some velocity. But what happens to the late electron? Late electron is traveling with the velocity greater than the V naught. That means this electron tries to overtake the reference electron. Similarly, early electron EE, that is slightly before the reference electron ER, that is subjected to a maximum negative field. That is subjected to the mobile already open cheyandamma. So similarly,
Yes, sir.
early electron EE that passes the gap A slightly before the reference electron ER, that corresponds to maximum negative field. So finally, you can say that reference electron ER is at point B, and late electron is point C, and early electron is at point A. So reference electron traveling with velocity V0, and late electron is traveling with velocity V greater than V0. Here, don't think that okay, more velocity, that's why it is early electron. Don't think like that. That electron is later when you compare with the reference electron. That's why that is known as the late electron. And one electron is and another electron is earlier than the reference electron. That's why that is known as early electron. So finally, here what happens? See, this is very important point. Because of the RF field, the velocity of the electrons changes. So the velocity of the electron varies in accordance with the RF input voltage. That process is known as the velocity modulation. That is very important definition. See here, early electron, late electron, and reference electron. So look at the applied diagram. So I want to open that. So this one. So here electron velocity changes, that is V greater than V0 and V equal to V0, V less than V0. So the velocity of the electron beam varies according to this RF signal. So that is known as, that process is known as the velocity modulation process. That is very important definition. Remember that. Okay. Now, as a result of all these things, the electrons in the bunching limit gradually bunch together as they travel down to the drift space from gap A to gap B. So because of this more speed, more velocity and less velocity, and all are not simultaneously at gap B, those are at different velocities, so different places. Okay, that's why I told that in sometimes more bunches, more number of electrons at one place, and some places sometimes not. And once again I am repeating, don't think that only 3 electrons are coming from the electron gun. More number of electrons, so more number of electrons are coming from the electron gun. Now, so the density of the electrons passing the gap B varies cyclically with time. That is, the electron beam contains an AC current and is current modulated, and you can say that the current is modulated. So here what I want to say is velocity modulation and current modulation. Velocity modulation and current modulation. So velocity modulation is at the buncher cavity, current modulation is at the catcher cavity. So while drifting from gap A to gap B, I want to show this diagram. Wait. So while shifting from gap A to gap B, here in this position, so velocity modulation, because here the velocity of the up to this point all are traveling with same velocity, but here what happens here, because of this RF signal, velocity of the electrons changes. So you can say that here the velocity modulation process, and that is drifting like this. Now at this position, so it can be converted into currents here. So current modulation. So in the drift space, current converted into velocity modulation to current modulation. So bunching occurs, and one more point is bunching occurs only once per cycle. For one complete cycle, bunching occurs only one and centered around the reference electron. So for that reason, in this applied diagram, I want to take only one cycle. So bunching occurs only once per cycle. And when you look at this applied diagram, here I want to assume that the time is TL here, late time and reference time and early time. So TL, TR, TE. So TE is more. That means velocity is less, right? So for this early electron, what is the velocity? Velocity V is less than V0. So velocity less than thing, but it is traveling with less velocity. Automatically, it takes more time. So whenever it is traveling with more velocity, it takes less time. Okay. That's why more time is required. More time is required. More time is required to travel through the drift space. So look at this position of gap A, and this is position of gap B. Actually, some mistake is there. Position of gap B here. So this is time taken by electron to travel through the drift space. So when you look at the diagram, this one, this is the drift space. The time taken for the electron to travel through the drift space. So more time is required for the early electron, and this is the reference time, and less time is required for the late electron. So the reason is for the late electron traveling with the more velocity, and early electron traveling with less velocity. So this is the applicate diagram of a Klystron amplifier. So finally, you can say that with the proper design of RF power, a small RF power applied to the buncher cavity results in a large beam current at the catcher cavity. This is the important point. I told that this cavity, this Klystron can be act as a amplifier. This two cavity Klystron amplifier, it can be used for the amplification purpose. So here what I want to say is a little RF power is applied at the buncher cavity. So because of the bunching process, and we know this. Yes, tell me.
Slide change అవ్వలేదు sir.
Okay, see here. Once again, I'm repeating that point, no problem. So two cavity Klystron amplifier, we know the meaning of amplification. So here finally what happened is at this position no bunching actually. At this position no bunching. But here what happens because of this RF signal. Suppose here I want to apply a small RF power signal. So small RF power signal, and because of this RF signal, here electrons are traveling with the different velocities, and all are bunched together, maybe at this point or at this point. So here what happens? Here only few electrons. So not bunching here, but here bunching is there. Yes.
Slide change అవ్వలేదు sir. But
Right here. So now finally you can say that I told that already bunching occurs only once, and the reference electron with respect to difference electron with the proper design of little RF power applied to the buncher cavity results in a large beam currents at the catcher cavity. So how can you get the amplified signal at the collector cavity is simple. Here at in the gap A, we are having the so many number of electrons, all are in the gap A. Velocity modulation process is there. So velocity modulation process nothing but RF signal is so combined with these electrons. Because of this RF signal, so these electrons are traveling with the different velocities. So all these electrons are bunched at this position or at this position. Now the electrons in the form of bunches, can be traveled to the gap B. So in the form of bunches it can be collected. So meaning of that is with the help of only one electron, with the help of two electrons is nothing but automatically less amount actually. So when you go for the bunches of electrons, so bunches of electrons nothing but automatically you can say that more power. So that bunches can be formed in the drift space. So whenever the electrons are traveling in the drift space, the electrons can be bunched together. Those bunches can be collected by the collector. That means you can say that in the gap A or in the input cavity, the electrons are single electrons actually, but coming to gap B, so bunch of electrons. That means you can say that in the input cavity less amount of power, and in the output cavity more amount of power. That means you can say that so amplified is there, so amplification is done. So like that RF signal is entering into this input cavity. Even with the low power signal, you can collect the with the proper design. You can collect the more current. That means amplified RF signal collected by the catcher cavity. Like that, this two cavity Klystron can be act as an amplifier. So same explanation you can also observe with respect to mathematical equations. So mathematical analysis. Now I want to give you the mathematical analysis for this two cavity Klystron amplifier. So the performance characteristics: first frequency 250 MHz to 100 GHz, 60 gigahertz nominal, and the power is 10 kilowatts to 500 kilowatts. So this is for continuous wave, and 30 milliwatts for pulsar wave. That means here when you go for the practicals, when you connect Klystron with the help of the microwave setup bench, sometimes you will get the sinusoidal signal and sometimes you will get the pulse signal. So if you go for the sinusoidal, that means continuous wave, the power is different, and when you go for the pulse, the power is different. And third one is power gain. Another performance characteristic is power gain. Here 15 decibels to 70 decibels, and here 60 dB is nominal. Power gain 15 decibels to 70 decibels. Now coming to bandwidth. Bandwidth 10 to 60 megahertz. So 10 to 60 megahertz generally used in fixed frequency applications. 10 to 60 megahertz generally used in fixed frequency applications. And fifth one is noise figure. 15 to 20 decibels, and sometimes greater than 25 decibels. Noise figure is 15 to 20 decibels, sometimes greater than 25 decibels. And finally, theoretical efficiency. Theoretical efficiency is 58%, and 30 to 40% nominal. So these are the performance characteristics of two cavity Klystron amplifier. Don't confuse actually performance characteristics for two cavity Klystron, reflex Klystron, traveling wave tube, all are available. Don't confuse. Confusion mainly while writing exams. So in order to get the full marks, you have to write the correct values. Remember that. Right. Similarly, applications where these two cavity Klystron amplifiers are used here. So you can use this as power output tubes. Power output tubes, that is in UHF TV transmitters, and in troposphere scatter transmitters, and satellite communications and radar transmitters. Satellite communication ground stations, and radar transmitters. I'm giving the applications here. So no need to write how can you use this in radar, how can you use this in satellite. That is a different topic actually. Here just I want to list the applications. UHF TV transmitters and troposphere scatter transmitters, satellite communication ground stations, and radar transmitters. So that is as power output tubes. And the second one is as a power oscillator. As a power oscillator, that is 5 to 50 gigahertz, used as a Klystron oscillator. As a power oscillator, 5 to 50 gigahertz is used as a Klystron oscillator. That means already I told that Klystron can also be act as an oscillator. If you want to use as an oscillator, the frequency is 5 to 50 gigahertz as a power oscillator, right? So that's it about the diagram of two cavity Klystron amplifier and the applicate diagram of two cavity Klystron amplifier, performance characteristics and applications. Now Put the heading as mathematical analysis of a Klystron amplifier. Mathematical analysis of a Klystron amplifier. Okay. Here, first I want to get the formula for velocity modulation process. First, I want to get the formula for velocity modulation process. And one more thing is, suppose whenever the question is, what is the velocity modulation process? Suppose if it is a 10 marks question, you have to draw the diagram once again, and you have to derive the formula for velocity modulation process, right? So, in order to get the formula for velocity modulation process, so I want to assume something. So, those assumptions are, let the DC voltage between the cathode and anode, DC voltage between the cathode and anode is V0. So, we are applying the DC voltage. Is it true or not? When you look at the two cavity Klystron amplifier, so battery is there. Battery is connected. So, negative terminal of the battery connected to electron gun, and the positive terminal of the battery is connected to collector. So, there is a DC voltage between the cathode and anode. So, I want to assume that DC voltage between the cathode and anode is V0, and small V0 is the velocity of the electron, and capital L is the drift space length. Actually, when you go for the like this, suppose you can draw the cavities like this also, don't confuse. So, this is one cavity, this is another cavity. Drift space, suppose this is drift space, this is L, okay, and the RF in, this is RF in, and this is RF out. Don't confuse. You can take the diagrams from the materials or from the textbooks. No problem. Don't confuse. Because here I don't want to waste the time by drawing all these things. So capital V0 is the DC voltage, and V0 is the velocity of the free electron, and capital L is the drift space length. And here you have to apply RF signal. You have to apply the RF signal to this, and the RF signal is passed through the through this input cavity or buncher cavity. I want to assume that RF signal is Vs. So finally, capital V0 is the DC voltage, and Vs is the RF signal, and L is the drift space length, and V0 is the velocity of the electron. Now, when the electrons are accelerated by the high DC voltage V0 before entering the buncher grid, now only I explained that before entering the buncher grid, and whenever those reaches the input cavity or buncher cavity, at that time only velocity modulation process is coming to picture, right? At the buncher cavity only. So because here, suppose here electron gun, we are having the electron gun here, electrons are coming like this, here velocity modulation process. So all this portion is before the velocity modulation process, or we can say that before the buncher grid. So when electrons are accelerated by the high DC voltage before entering the buncher grid, their velocity is uniform. Already I told that. So all are traveling with the uniform velocity. Whenever those are entered into buncher cavity and those are combining with the RF signal, then only the velocity of the electron changes. Like high velocity, suppose V0 greater than V0, less than V0, equal to V0, like that. But before the buncher grid, all are traveling with the uniform velocity, and that velocity is V0 equal to root of 2q capital V0 by m. And already told that is equal to 0.593 into 10 power 6 root V0 meter per second. So this is equation number 1. So this equation 1 is the velocity of the free electron before the buncher cavity. So these are very, very important. So before the buncher cavity and after the buncher cavity. So before the bunch, and one more thing is if you want to talk about the velocity modulation process, you have to go for at the Buncher cavity or after the Buncher cavity. So before the Buncher cavity, there is no velocity modulation process, because velocity modulation process is nothing but, so whenever the RF signal is interact with the electrons, so the RF signal interacts with the electron only in the Buncher cavity, not before the Buncher cavity, right? Next, already I told that I want to apply the RF signal as RF signal, and the RF signal is Vs, and Vs is equal to, suppose, some V1 sin t or sin omega t, V1 sin omega t. Suppose this is equation number 2. Remember one thing, you have to draw this diagram also, but I don't want to mention this diagram because already I have given to you. So two equations, one is the velocity of the free electron. So look at the order also. Look at the order also. First, before the bunching electron, now electrons are like this up to this with the uniform velocity. Now the RF signal like this. So I want to assume that RF signal as Vs, Vs is equal to V1 sin omega t. That is equation number 2. Right? Now I want to find the average microwave voltage in the buncher gap. I want to find average microwave voltage. The average microwave voltage in the buncher gap. In the buncher gap. So how can you find the average value of a function actually? Suppose the limits are t1 comma t2, signal is x of t. How can you find the average? 1 by t2 minus t1 integral t1 to t2 x of t dt. Like that here also, the average microwave voltage in the buncher gap. So the buncher gap nothing but average value nothing but this one. Voltage nothing but is signal voltage. So signal is RF signal. RF signal nothing but Vs. So I want to find the average value for this Vs. So I want to write the average value like this. So Vs is equal to 1 by so I want to take the times are here T1 and T2. So T1 and T0. So here, so this is the diagram, right? This is the diagram. So in this diagram, so up to this I want to assume the time is T0, and at this point time is T1. Look at this. See the drift space here L here. So this is the initial point 0, and this space is D. This space is D. Now this is the distance L. Now what happened? This is the L plus D. This is L plus D. Again, this space and this space is same. So this is also D. That's why this is L plus 2D. And at the time up to this point time is T0 here. Now this is the point time T1, and here T2, T3. Just I want to assume like that. Don't fix this all these times. I want to assume like that. And this is the R in, and this is the R off. Right? Now with this. So with this now see here. So average microwave voltage. With this, the average microwave voltage in the buncher gap can be obtained like 1 by, what is the final time at T1 in the buncher gap only. In the buncher gap only, T1 minus T0. It's like T2 minus T1. T1 minus T0 integral T0 to T1. Signal is Vs dt. That is equal to 1 by T1 minus T0 integral T0 to T1. So V1 sin omega t dt. That's it. Now that equal to 1 by T1 minus T0. I want to assume this as a tau. So tau integral directly after integration V1 sin nothing but I think minus cos. So minus here, and this is T0 T1. So after substituting the limits, I want to write the right answer. After substitution the limits, you will get V1 by by omega actually. V1 because sin omega t minus cos omega t divided by omega. So V1 by omega tau into cos of omega t naught minus cos of omega t1. So this is the equation after integration and after substituting the limits. Okay. Repeating once again. So average microwave voltage Vs is equal to V1 by omega tau cos omega T1. Here what is V1? Don't confuse about the V0 and V1. Capital V0 is the DC voltage and V1 is the, what is capital V1? Now I want to know either you are following or not. What is capital V1? Yes. What is capital V1? Don't know? Hello.
Sir,
What is capital V1? Right. So V1 is the your amplitude of RF signal. Don't confuse capital V0 because when you go for problems, so all these are very very important. They used to mention like amplitude of RF signal is something and DC voltage is something. So all those things you have to substitute into the formulas. Suppose if you substitute in place of V0 V1 in place of V1 V0, definitely you will get the wrong answer. So in order to get the correct answer, in order to get the good marks, you have to remember each and everything, and you have to know what is what, right? So finally, average value Vs is equal to V1 by omega tau. Again, when suppose nobody is ready to answer means no one is listening. I think all are enjoying. Right after this equation, now already we know that the transit angle theta z is equal to what is the formula omega tau z, right? Transit angle theta is equal to omega tau z or omega into, in this case tau is nothing but here my consideration is t1 minus t0. That equal you can write omega into, when you go for the transit time effect, d by v0. D by V0. See, don't confuse here because now only I shared a image to your WhatsApp. When you observe that the space between the space in the cavity is nothing but d actually, d, and the velocity of the electron is equal to V0. So you can write d by V0. So theta g is equal to omega d by V0. Now when you substitute this to above equation, that equal you can write V1 by omega t cos omega t naught minus cos omega t1. In place of omega t1, I want to write omega t naught plus omega d by v naught. Is it okay? So from this, omega t1 equal to omega t naught plus omega d by v naught. Now I want to assume that let omega t naught plus omega d by 2 v naught is equal to a. That means that equal to you can write omega t naught plus theta z by 2. Because theta z equal to omega d by v naught and omega d by 2 v naught, that means you can write theta z by 2. So finally you can write a is equal to omega t naught theta z by 2. This is just for simplification purpose because every time it is not possible to write all these lengthy equations. For that reason I am writing like this. And omega d by 2 v naught equal to theta z by 2 and that equal to b. So finally I want to assume that a is equal to omega t naught plus theta z by 2 and b equal to theta z by 2. Now by substituting all these things into above equation, you can write v1 by omega tau cos of omega t naught. Actually we are having only omega t naught, but I want to write in terms of a and b. That's why I want to add and subtract with theta z by 2 minus cos omega T naught plus. Actually, omega D by V naught. Omega D by V naught nothing but only theta Z. In place of theta Z, I want to write theta Z by 2 plus theta Z by 2. Because here my assumption is A and B, I want to write in terms of A and B. That's why I want to write all these things. That equal to finally V1 by omega tau. So cos omega t plus theta z by 2 minus theta z by 2. Cos omega t naught plus theta z by 2 minus plus theta z by 2. What is the meaning of this? Cos of A plus B minus cos of, so cos of A minus B minus cos of A plus B. Right? Cos of A minus B minus cos of A plus B. What is the formula? 2 sin A sin B. A nothing but here omega t naught theta z by 2 and sin theta z by 2. And from this V1 by omega 2V1 by omega tau nothing but again you can write tau is d by V naught. So this whole thing. This whole thing. And that equal to finally you can write 2V1 by directly I want to write the answer. So V1 into sin theta z by 2 by theta z by 2 into sin omega t naught plus theta z by 2. Because omega d by V naught, again omega d by V naught nothing but omega d by V naught nothing but theta z, and here in place of this you can write V1 by omega d by 2 V naught. Omega d by 2 is nothing but theta z. So V1 by theta 2 theta z. That's why you can write V1 into sin theta z by 2 by theta z by 2 into sin omega t naught plus theta z by 2. Here omega d by V naught equal to theta g. Okay. So after this, first let me clear one thing. మీరు నోట్ చేస్తున్నారమ్మా చెప్పేది? అంటే ఎందుకు అంటే okay, now just 5 minutes. Now let beta I equal to sin theta z by 2 by sin theta z by 2. Now again this is the important point, an important coefficient. Beta I equal to sin theta z by 2 by theta z by 2. So this is known as beam coupling coefficient. Sometimes in the problems question is calculate or obtain beam coupling coefficient. Beam coupling coefficient of the input cavity gap, because here I am talking about the buncher cavity. I am talking about the buncher cavity. So of the input cavity gap. I am not talking about the catcher cavity up to now. I am talking only about the input cavity or buncher cavity. So let beta I equal to sin theta z by 2 by theta z by 2. So it is beam coupling coefficient right. Now here, for example, if you increase the theta g, then what happens? Whenever theta g increases, then what happens? If theta g increases, there is increase in the gap transit angle theta g, then automatically the coupling between the electron beam and the buncher cavity is decreases. Right? That means beta I, whenever theta g is increases, beta I is decreases. That means you can say that what is beta I? Coupling coefficient. So beta I is a coupling coefficient. That's why you can say that increasing the gap transit angle theta z, decreases the coupling between the electron beam and buncher cavity. That is, velocity modulation of the electron beam for a given microwave signal is decreased. Coupling coefficient is decreasing. Coupling coefficient decreasing means, what is the meaning of that? Coupling nothing but here. So there is a combining of RF signal and electron beams. If that coefficient is decreases, the velocity modulation process for a given microwave signal is decreased. Okay, remember that point. Now continuation. Now finally you can write the average value Vs is equal to beta I. So beta I nothing but here sin theta g by 2 by theta g by 2. Beta I V1 sin omega t naught plus theta g by 2. Right? Now the exit velocity at buncher cavity. The exit velocity at buncher cavity. That means here what I want to say is the energy of the electron at the time of leaving buncher cavity. The energy of the electron at the time of leaving the buncher cavity. Up to now I am talking about in the buncher cavity. Now I want to go for the electrons are leaving the buncher cavity. That's why exit velocity at buncher cavity. So when you go for the exit velocity at buncher cavity, then what happens? Automatically, definitely, the RF signal also comes into picture. The RF signal also comes into picture after the buncher cavity, because within the buncher cavity only velocity modulation process occurs. Now the exit velocity at buncher cavity is 1 by 2 m v1 square is equal to q v0 plus beta I v1 sin omega t naught plus theta g by 2. Actually, previous formula is v0 equal, right? V0 equal root of 2q v by m. 2q v by m. But here not I am taking the v0. Here I want to go for the v1 here. V1 is root of 2q v by m. But here what happens in previous case? Only v0. Only v0 nothing but only DC voltage. So I am repeating once again. Before the buncher cavity, because of the applied voltage, because of the DC voltage V0. But what happens within the buncher cavity? DC voltage and as well as the RF signal voltage also comes into picture. So average RF signal voltage. What is the RF signal voltage here? Vs. So Vs is equal to, what is the final formula? Beta I V1 sin omega t naught plus theta g by 2. That means here what happens? DC voltage plus RF signal voltage. For that reason, I calculated the RF signal micro signal average voltage. That is beta I V1 sin omega t naught plus theta g by 2. So okay, but previous formula is, what is the equation 1? I think that is only V0 equal to root of 2q V0 by m. V0 is the only DC voltage, that is before the buncher cavity. But here I am talking about after the buncher cavity, exit velocity of the buncher cavity. So the exit velocity of the buncher cavity nothing but here you have to consider DC voltage and as well as the RF signal voltage also. So the average value of the RF signal voltage is beta I V1 sin omega t naught plus theta g by 2. That's it. Clear about this? And one more thing is, here I want to assume that V1 is the velocity or exit velocity of the buncher cavity, and before the buncher cavity velocity is equal to V0. Before the buncher cavity velocity is equal to V0, and after the buncher cavity I want to assume that velocity is equal to V1, because the velocity changes. The velocity is not uniform after the buncher cavity. Now from this, V1 square equal to 2q by m, take V0 as common, 1 plus beta I V1 by V0 sin omega t naught plus theta g by 2. And from this, V1 equal to root of 2q V0 by m into 1 plus beta I V1 by V naught sin omega T naught plus theta G by 2. And that equal to, from equation 1, I think, to root of 2q V naught by Vm nothing but this is small V naught, velocity of the free electron or before the puncture cavity. Finally, V1 equal to V naught into 1 plus beta I capital V1 by capital V naught. Don't confuse. Capital V naught is separate and small V naught is separate, and capital V naught is the DC voltage and capital V1 is the amplitude of the RF signal, and small V naught is the velocity of the electron before the puncture cavity, and V1 is the exit velocity of the electron after the puncture cavity. 1 plus Bi V1 by V naught sin omega T naught plus theta G by 2. I think here we are having a 1 by 2, right? V1 equal to root of 2q V naught by M, the root of 1 plus like this. So here actually here one binomial expansion is like 1 plus x4 1 by 2, that equal you can get 1 plus 1 by 2 x plus up to so on. I want to neglect the higher order terms, you can get only 1 plus 1 by 2 x. Okay, 1 plus 1 by 2 x. That's why I want to write here by 2 V naught. 1 plus beta I V1 by 2 V naught into sin omega T naught plus theta G by 2. This is by neglecting higher order powers or higher order terms. So finally, V1 is equal to, this is after the puncture cavity. What is the meaning of that? This is after the velocity modulation. So this V1 equal to V naught into 1 plus beta I capital V1 by 2 capital V naught sin omega T naught plus theta G by 2. This equation is known as velocity modulation equation. So while the question is explained about the velocity modulation, you have to write up to this equation. I'm repeating once again, depends upon the question, you have to write the answer. Velocity modulation. The velocity modulation equation is V1 equal to V naught into 1 plus beta I V1 by 2 V naught sin omega T naught plus theta G by 2. This equation known as velocity modulation equation. For example, I want to assume that beta I V1 by V naught, beta I V1 by V naught. So this equation or this term is known as the depth of velocity modulation. So previous one is coupling coefficient, beam coupling coefficient, that is beta I. Now beta I V1 by V naught is depth of velocity modulation, and this equation is the velocity modulation equation. And one more point is always beta I V1 is less than V naught. Is it or not? When you go for the DC voltage may be 5 volts, 10 volts, 20 volts, 30 volts, 50 volts like that. But coming to RF signal, you can't take 50 volt signal, right? Is it true or not? Because if you take 50 volt signal, how can you amplify that? So in order to amplify that, you have to take only small powers. You have to take only small powers. You have to consider in order to amplify that small values. So beta I V1 is always less than V naught. Remember the conditions also. So how can you get this condition? Nothing but simply with your knowledge only you can say the answer. Capital V naught is the DC voltage. Always DC voltage, we know the DC battery, that is 5 volts, 10 volts, 30 volts, 40 volts, 50 volts like that. And coming to V1 is the amplitude of the RF signal, and that is a lesser value. Already we know that beta I value is also less. So when you multiply those two also, you will get the less value. That's why beta I V1 is less than V naught, and the term beta I V naught by V naught is known as the depth of velocity modulation. Right? That means when you observe the two cavity Klystron amplifier, so before the puncture cavity and within the puncture cavity, after the puncture cavity, up to that point is completed. Any doubts?
No, sir.
Okay, remaining in next class.
Okay.